So hello and welcome to this Arrow lecture looking at materials of challenging environments, specializing in nuclear materials. And in this mini lecture we focused on nuclear fusion. So I'm Dr. Sandy Knowles. I'm a UKRI Future Leaders Fellow, Royal Academy of Engineering Research Fellow and an Associate Professor in Nuclear Materials at the University of Birmingham in the UK. So my research specialism, I spend a lot of my time working in developing new materials for fusion. There's a lot of challenges to overcome, but also a lot of opportunities, and it's a very exciting research area to be in, and a lot of progress being made. And with the kind of initiatives going on, both from state-sponsored efforts for fusion, as well as investments from the private sector, there's a lot of work to do, and a lot of people focused into this area now. So thank you again to Arua for the invitation to give these lectures, and also to GCRF and UKRI for supporting this initiative.
So nuclear fusion energy, what is it? Why do we want it? So ultimately it's the energy source that powers the sun, multiple different fusion reactions that create huge amounts of energies that really power everything else in our solar system. On Earth it's not as easy. The sun is very large and has very high gravitational energy, so a lot of constraint. There's a large mass, and so that puts a lot of pressure, and that gives us different stability of different reactions. So on Earth, if we want to have a controlled fusion, particularly we do it through using deuterium and tritium. So these are hydrogen isotopes with excess neutrons. And if we can get to the right temperatures, so we're talking over 100 million Kelvin, so it's sort of 10 times hotter than the sun. So that we have to go hotter than the sun because we don't have that physical constraint with the gravity that we have on the sun. And if we can get deuterium and tritium to fuse together, then this reacts to create helium. So we've got this reaction on the bottom right. So deuterium plus tritium, which gives us helium, it gives us neutrons and a lot of energy. So we're kind of thinking of Einsteinian reaction equals mc squared. We get this slight change in mass, but then that releases this massive amount of energy. And so if we could really harness this deuterium-tritium, so what's called the DT reaction, and use that as an energy source, it really offers the prospect of near unlimited energy production with no long-lived nuclear waste. So this is the real kind of holy grail energy source. And I think what's exciting is that we know it's possible, and I think the transition at the moment is from the possible to the practical. So it is really this transition from science to engineering. So there's this kind of joke around kind of fusion and fusion always being 50 years away, and I think it was just last year or so was officially 50 years since a group of British scientists went to Russia and brought back and worked together with the Russian scientists and to extend the tokamak concept. And when they came back to the UK, they proclaimed fusion is 50 years away from being an energy source. And so we've had some huge successes in fusion. So the JET, the Joint European Torus, which is at Columbus Centre for Fusion Energy, is a European endeavour to extend fusion. So since 1996, it's been operating and has held the record for fusion energy. So generating 16 megawatts of output from 25 megawatts of input. Critically, the output is lower than the input, but we can generate fusion reactions to give out energy, and that is a major breakthrough. And so this success in JET of at least being able to prove the tokamak concept, prove that you can generate a plasma, has led to the kind of motivation to go through to ITER. So this is International Test Reactor, which is European, well actually international. It's all pretty much all nations involved: Europe, America, China, Russia, South Korea. There's many, Japan, all involved. So many countries involved to make this a reality. And the pledge from ITER, which is expected to be finished about 2025, is that we're going to get 500 megawatts of output power from 50 megawatts of input power. So this really kind of changes the game. Now we really know that we can get energy out. And the follow-up to that, which is already planned, and a few countries have also planned their own derivative versions of these. So particularly, I think definitely China, South Korea, and I believe America have all committed to doing demo 2, 3, 4. And these are expected to hopefully be built around 2050 as the so-called demonstrator power plants, which would give about potentially 2 gigawatts power output which really makes them competitive, at least on power, compared to current fission reactors. So hopefully, we can get the economics right on that, as well as the scientific basis. So I think, really, for me, it's quite an exciting time in fusion because, ITER is really still probably a science, it's almost a science experiment. But really, through ITER, we're really on this transition from just doing plasma physics, science, fundamental work, almost like CERN and the Higgs boson. But we're really kind of going towards an engineering goal to generate power. And I think really over this decade, we're seeing that transition just from plasma physics problems towards engineering challenges, and then really trying to make this a practical energy source. I think there's a huge degree of likelihood of success in this concept. 2050 is a long way away, but not that long when, in terms of the scale and the technology that has to be developed to make it happen. We would like to go quicker, I would say, and there are multiple efforts to try to do that. So I think there's around 10 different startup companies working in fusion energy, as well as multiple national labs that have different technologies to what I'm showing on the top. So one to mention would be the National Ignition Facility in America. I think it's called Spark Energy, which is an MIT spin-out. And in the UK, we've got Tokamak Energy, so also kind of near to Oxford is where it's based. And we've got, it's CCFE, what's called the STEP program, so Spherical Tokamaks for Energy Production. And particularly from Tokamak Energy and STEP, they're using a much smaller reactor concept. And one of the ideas there is that if you go smaller, you can iterate quicker and potentially get there faster. So both concepts are proposing that we hopefully will demonstrate feasibility of these concepts by 2030. We may even be able to get power onto grid significantly before 2040. So we might even be able to halve the time it takes to get to functioning power plants. So these are much smaller, so they're smaller energy per reactor, but you could have many of them kind of similar to the advanced modular reactors that's kind of talked about a lot in kind of the small modular reactors and advanced modular reactors in kind of more fission context. But this leaves us with a challenge across all of these. We could design a beautiful reactor, but what are we going to make it out of? And really, what materials can withstand 20 years in a fusion power plant? It's a hugely aggressive. It's wonderful that we have these hugely high energy neutrons, but they also can do a lot of damage and put in a lot of heat to the materials, which makes it a challenging environment. So I just want to kind of go into a bit more detail on ITER. So this is a reactor that's physically being built at the moment. So if you go onto the ITER website, you'll see fascinating videos and information about how it's being built and put together. There's some awesome things about this reactor. So just for a sense of scale, at the bottom there is a person. So this thing is a phenomenally big reactor and big engineering project. So I think we've been designing ITER probably for about 20 years now, and I think site was broken at least 10 years ago now. And we hope within 5 years we'll have a functioning reactor and one that is going to break records for amount of energy output. So within that we have some amazing things. So we have the central kind of inverse donut, so the tokamak, and our plasma, which is kind of rotating through the central column. So in order to control that plasma, we have hugely strong magnets. So we have the central solenoid, and we have then circumferential ones. And each of these are the biggest magnet in the world. At the time, so it's niobium tin is one of the superconductors. The amount of superconducting material that ITER currently uses is 10 times what annual production was 10 years ago. So they had to increase the world production of the superconductor in order to be able to build this thing. So it really shows kind of not, the scale of the thing to make these things at this size and the time it takes and the money it costs. So I think this one's on the order of 20 billion to construct it. It's a huge investment, and that's really one of the things that's motivated all countries to work together to a common aim, is because it's almost too expensive for one country to do it alone. And I think in that regard, it's a real success to, kind of current climates to have countries working together, and that has its own benefits. So I wanted to kind of talk a bit more detail in terms of, so what are the demands in fusion? Well, ultimately, it's a very hot, so we've got 100 million, 150 million degrees C fusion plasma. So a majority of that heat is confined by the magnetic field, but ultimately this still is a physical thing at some point, and that will be exposed to significant heat, partly because we want it to, right? We want to extract energy from this reactor, therefore we need to heat something up. And there is going to be some extra challenges or design to how to extract that heat effectively and efficiently. But we have very high heat. We have neutrons that are produced by the fusion reaction, and those neutrons have much higher energy than in current fission reactions. And that means both that they will penetrate deeper into the material, but also just the damage that they create because they have more energy is more significant. So the damage doses we'll see in fusion haven't been experienced in current fission reactors. So we have also this neutron damage. Depending on the location in the reactor, we have different concerns in terms of the environment. So in the kind of first wall, then we have exposure to hydrogen and to helium, which are going to implant into the material and might damage the first wall materials. And then elsewhere in the material, in the reactor, we're going to have different corrosive environments. So maybe we're using water cooling, maybe it's helium or supercritical CO2 or molten metal, molten salts. So we have a lot of shared challenges there with Gen 4 in terms of corrosion problems paired with high temperature and neutron radiation damage. But we have, at least for ITER, we kind of know what we're going to try and make it out of. Certainly these are not perfectly optimized. We're stuck in a bit of a situation with fusion where we have to make it out of materials we have, not necessarily out of the materials we would want to have. And I'll talk about that a bit more in a moment. So in terms of the structure, so everything needs to be held together. It's also some level of confinement. It also needs to be highly formable. It's a large structure. It needs to have complex shapes. Here we pretty much don't have much choice. It's almost got to be a steel in terms of just the tonnage of material we need. So ITER is going to use more steel than the Eiffel Tower, which I just find is a phenomenal comparison in terms of the scale of this project. So even on a project as expensive as this, cost is still a concern. It needs to be high strength, it needs to be tough, and again, this formability and joinability. So the fact that we can manufacture steel at such large quantities and the fact that we can weld it together gives huge advantages. We then go on to the magnets. So again, we mentioned these are kind of critically there to contain the plasma. They're also used to introduce and remove, or introduce the fuel and remove the waste. So there's a complex magnetic flux lines to induce a flow in the plasma, to put fuel in and take waste out. So we're using this niobium tin type 2 superconductor, so it allows us to have large fields, large fluxes. But yeah, as mentioned, that we had to scale up world supply in order to be able to supply it. Certainly, say for example, in all of these there are further developments. So, say for example, STEP and talking about energy, they use some slightly more advanced superconductors, and I'm sure that technology then will feed into demo, not necessarily using the same superconductors. There's a lot of improvements that can be made there. And are niobium tin superconductors optimized for fusion in terms of irradiation damage? Probably not. We've got the first wall. So we mentioned that most of the confinement in terms of temperature comes from the magnets, but it still does need to get close to a physical material. So in JET we were using beryllium and some places tungsten. In ITER it's pretty much going to be a full internal structure of tungsten, at least a few millimeters thick. So there are a few things going on there, and actually, because these have been science experiments, one of the key requirements has been to avoid poisoning the plasma. You actually want something that either is very light, low Z, or light element, that if it goes into the plasma doesn't disrupt the plasma, or something that's very high Z, therefore it's just very ablation resistant. And tungsten, being very ablation resistant, being very high melting point, it wins on both of these. Another criteria is what happens when you implant it with neutrons, so the neutron damage. To be honest, tungsten isn't perfect, but we'll have to live with it. And there's some definite engineering design needed to improve the irradiation damage resistance of tungsten. So we've been running yearly master's projects with Columbia Centre of Fusion Energy to work on improved tungsten alloys. So both master's project and PhD projects. I guess the other thing is just the implantation of hydrogen and helium, and actually tungsten is quite good in that regard. It's got quite low solubility for both, so it doesn't absorb as many as say, titanium might in comparison, or zirconium. We've got diverter, so this is even higher heat flux and helium flux compared to the first wall. So here, this is actually where we take out the waste, the helium ash from the reaction. So this is where the flux lines from magnets converge, and the plasma all impacts the diverter. So this has the most severe heat flux and this implantation with helium. So I think really the only option here is tungsten, and it's pretty much a process of elimination of what you can't use. So we did consider for many years carbon, so graphite would be kind of the analog there, and it was calculated that if you did have a graphite diverter, the erosion rate would be 1 meter per year. So you would pretty much need to be constantly replacing your diverter and using it as a consumable. And obviously all of that carbon then goes into the fusion plasma and will become activated. So it's not an ideal solution. Silicon carbide might be a possibility, but as with tungsten, very significant toughness and cracking issues. But tungsten has cracking issues of its own. And the key kind of challenge here is avoiding the ablation. And one which I think is kind of, still many questions to answer is on the tritium breeding module. So we mentioned that, the idea of fusion is that we have kind of almost unlimited energy. And that comes really from this reaction with deuterium, which we can very easily extract from seawater. But tritium is a bit more sophisticated. It's not so easy to just extract that from nature. And actually, the way we need to do this in fusion is to generate our own tritium by the reactor. So you can have a reaction between neutrons and lithium, which create tritium. But in order to do that, you need to get neutrons from your reactor into a tritium breeding module in order to react with lithium and nuclear reaction with lithium to generate tritium. And so you need some low neutron cross-section materials, you need high flux, high temperature, and low neutron cross-section. So as well as then designing the whole component and how the environmental resistance, what's your coolant, things like that. So we currently have a couple of projects looking at low neutron cross-section fusion materials, particularly towards tritium breeder module. And I think that's also something we'll be continuing on. I guess, a lot of the demands we've been kind of spelling out here for fusion have a lot of analogy with Generation 4 fission. It's quite strange that the two communities are working quite separately. I guess they have different end goals, different timelines, different budgets, I think is the fundamental thing. But the kind of challenges in terms of high temperatures and the coolants, there's many commonalities. I guess one of the things which I would highlight as the key difference is the waste disposal aspect. So in fusion, we have this mandate to try and create fusion reactors that do not create any long-lived radioactive waste. And so this is a periodic table for elements in terms of how long it would take them to become low-level radioactive waste after they've been within a fusion reactor. So 14 years of operation within demo. If things are in red, then we kind of maybe wouldn't want to use them in our fusion reactor, or we need to look in more detail in terms of the neutronics and the activation. And the real challenge here are that a lot of things in red are really the things that we want to use in engineering alloys. So we very often are using nickel, we very often are using molybdenum, and particularly in steel. So particularly, say, for example, P91, which is a ferritic martensitic steel that's widely employed or being employed for Generation 4 fission. And particularly we have molybdenum and niobium, which are kind of complete no-nos in terms of fusion. So in the fusion design space, we then say, okay, well, maybe we can exchange molybdenum for tungsten, and maybe we can exchange niobium for vanadium, and that kind of is how we get to what's called these reduced activation ferritic martensitic steels. So Europa is sort of the leading example of that. And as a metallurgist, someone who works on these kind of materials, it's, that there's some commonality in how different elements act when you alloy them into material, but it's not straightforward, and there's still significant development. We haven't yet got RAFMs that are as good as, say, P91. And I think there's a real kind of need to iteratively learn from one another. So why is it that the Gen 4 steels are still better performing than our fusion-specific steels, and how can we improve the fusion steels further? And so that's one of the things that sort of we work on in the group, is both improving alloys that we might want to use, but really a lot of what our work in the group is saying, okay, well, let's just throw out the towel, let's start and let's use something just tungsten alloys or just chromium alloys, looking at things that haven't been pursued for Gen 4, that maybe are motivated by fusion, but could also be beneficial for both applications. So that's a lot of what we do in my group is looking at completely new materials to start from scratch and zero assumptions, and try to develop a new material that really will enable this high temperature, high neutron flux and aggressive corrosive environments and successfully withstand those conditions. So there's a lot of work, and we need to take probably both a fundamentally new approaches as well as iterative approaches, and it's not a one solution problem. And I think for me as a fusion and nuclear researcher, there are a lot of open questions, but also a lot of opportunities. So it's a very interesting research environment. So I hope you found that kind of interesting, kind of this outline of where we're up to on fusion and some of the materials challenges for fusion. So see you in the next session.